Is my screen visible? Can someone just confirm? Okay, excellent. So let's continue with the discussion that we have been having in the last class around international reference ellipsoid. So we said that we can approximate the shape of the Earth by means of an ellipsoid, right? And we said that we can define the major axis of the ellipsoid as A and the minor axis of the ellipsoid as C. Okay. So the value of A, what have people, and I explained how the ellipsoid is essentially drawn from the GPS data in the last class. So the value of A, what people have found, is around 6378.136 kilometers. And then the value of C, sorry, A and C are the half of the major axis. My apologies. Okay. And C is 6356.751 kilometers. Now, we said that we need to essentially draw an equivalent circle, right? You remember? Or an equivalent sphere. Okay. And then we said this, the radius of the sphere is R. So R can be found out by A square by C. And that will provide you around, the value of R will come down to 6371, approximately 6371 kilometers, okay, which we generally use as the radius of the Earth. Okay. We talked about the flattening, okay, and we said the flattening is A minus C by A, and that is 1 by 298.252. Okay. Now, what people had theoretically shown that if the Earth would have been a perfectly rotating fluid, yeah, then the value of A would have been 1 by 299.5. Now you can see there is a bit of difference than the flattening that we observed in case of the Earth than if it would have been a perfectly rotating fluid. So that means that it's not, I mean, we know from our experience, of course, the crust is not a fluid, right? So the rheology, there is a change in rheology, there is a difference in rheology along the radius of the Earth. Okay, so we can also say that the Earth has more strength than a fluid, right? So what does this word strength means? We will explain later on uh, while we discuss seismic, and this is a rheological term. Okay? Rheological term, and rheology means the effect of a material when it is subjected to stress. To stress. And stress is nothing but force per unit area. So strength is a rheological term, and this refers to the effect of a particular material when it is subject to stress. Okay, and we will, uh, talk about material strength in greater details while we talk about seismic. Okay, in the introductory part of the seismic lecture. So for the time being, you can imagine a solid has a more solid is stronger than something which is brittle or solid. Rigid is more stronger than a fluid. Okay. Now, what is the cause for this flattening, or we can also call it as polar flattening, right? So, what is the cause of this polar flattening? Let's try to find out the answer. Okay. So you remember while we were trying to prove the Kepler's third law, what we did, we have taken the centripetal acceleration exactly equal to the gravitational acceleration. Remember, and then that's how we had calculated that Kepler's law to be true. So one of the fundamental assumptions in those calculations that the Earth is a perfect sphere. That is our fundamental assumption, or any planetary body that we deal with in such calculation. We think that it is a perfect sphere, but we have just seen it is not the case. So if it deviates from a sphere, uh, so the assumption, the general assumption is Earth is a perfect sphere. Okay? Now we have just seen that this is, and if we go with this assumption, we can say that the centrifugal acceleration, so AC, centrifugal acceleration, is equals to AG. If this particular assumption is true. But we have just seen that this assumption is perhaps not true. We have just proved that from our GPS data, right? And what we observed then, that the centrifugal acceleration, AC, yeah, is maximum is maximum at the equator is maximum at the equator, and AG is minimum at the equator. Okay, so we can express the ratio. Okay, we can express the ratio of the AC at equator by AG at equator with a value called M, and we see that the value comes around 1 by 88.901. Okay, so this has another type of inference. The inference is that the distribution of mass, and this is another very important inference that we are going to use in our course. And remember this particular inference, that the distribution of the mass is not purely a function of the radius. Okay, so what do I mean by that? I mean, I take the liberty of using some part of it in draw. I mean, if I think of a perfect sphere, okay, then this is crust, a very top part of the crust, and then we say there is mantle. Let's say this part is mantle, and then core. So crust, mantle, right? So if this would have been a perfect sphere, we would have thought, yeah, I can say that the crust has a lower density, the mantle is heavier, core is even heavier. So I can see that the distribution of mass is strictly a function of radius. So if we go down, I see heavier mass, right? But then, of course, if it is not a perfect sphere, we can see that in some places there will be a thinning of crust. Some places we see a thickening of crust. And then, of course, what we will observe that, the shape of and then on the top of it, I have this polar flattening, right? So all these things will essentially lead to this inference that the distribution of mass is rather ununiform, yeah, in the Earth. And that will provide us some very straightforward ways of using the gravity technique for our own purposes. Okay, now let's get into another important. I mean, we'll continue with the same thing, but let's expand the theme a bit more. Okay. Let's first draw a sphere which is represented. Sorry, let me just do the thing, link to shape, so that I can draw a perfect sphere. I'll try. Yes. Now, to draw the sphere in 3 dimension, what I need to draw, I need to draw the equatorial plane. So this is the equatorial plane of the sphere. Okay. Let's just put a dot so that I understand it properly. Let's define some axis around it. The perpendicular axis. Let's call them X, Y, and Z. Okay. Now, let us say the moment of inertia along Z axis is T. The moment of inertia along Y axis is B, and the moment of inertia along the X axis is A. If this would have been a perfect sphere, of course, A, B, and C would have been equal. But that is not the case, of course. So this will not be a perfect sphere, right? So if this is not a perfect sphere, then A, B, and C will not be equal. And how much anisotropic this moment of inertia is defined by, so the anisotropy in the moment of inertia is expressed by term called dynamic ellipticity. Okay? Dynamical ellipticity, my apologies. And dynamical ellipticity H is defined as T minus half of A plus B by. Now, to make our life little easier, let us say at the equatorial plane, A and B is equal, okay? So it's just for the assumption, okay? What we have observed in the Earth, A and B is not equal, but the difference is not also that large, okay? So A is closely equal to B. We are trying to make our life a little more easier, and we are saying that A is equals to B, and by that we can find out H is closely equals to C minus A by C. Okay, and the current optimum value of H, okay, what people have found out is around 3.2737875 into 10 to the power minus 3, or a better way of writing it, just to be similar to the other expressions, 1 by 305.457. Okay. Now, with this in mind, one famous scientist called J. McCulloch J. McCulloch in 1849 expressed the gravitational potential with the following formula. So he has given the following formula: UG is equals to minus GE by R. Now, this part we all know, right? This we have already deduced that gravitational potential is equals to minus G E by R, right? GM by R. So M can be replaced with E, and E is the mass of the Earth, right? G by R. Now, this is for a perfect sphere. Okay? This part is for a now. What was the contribution of Maculag? Was essentially to, you know, think about the ellipticity that think about the flattening that the Earth might have, and he actually introduced another term to get closer to the gravitational potential: E A plus B plus C minus C I divided by 2R cube. Okay? And I is, say, for example, I'll explain this part, and he left it there. I'll explain why I am doing this. And he expressed that I is, I'll draw the picture again for you. Not the, sorry. So we said this is C, this is B, and this is A, right? And so if I want to calculate the moment of inertia at any point P, which is situated at a distance of r from the center of the Earth, and making an angle theta with the z-axis, and I can explain. I can get the position of point P with the polar coordinate system r theta. So the inertia, uh, the moment of inertia at point P is defined as I. So this is what he has given. Now this is based on, you know, thinking that the Earth, so this is for a perfect sphere, and then you add this term to actually, uh, so this term plus this term together provides me Earth being, sorry, this is Earth is an ellipsoid. No further complications. Sphere, and then its deviation due to flattening, you know, a regular flattening, I get an ellipsoid. And to account for the gravitational potential, I can actually subtract a term which is expressed by a plus b plus c minus 3i by 2r.
So, in the original gravitational potential of a perfect sphere, uh,
Mm-hmm.
we had the small r as the radius of the Earth, right?
Yeah, I mean, if you so r you can think of if you are calculating the gravitational potential at the surface of the Earth. Okay, then this is capital R. So if you are moving away from it, you understand, then it is R. I mean, it will be capital R. So let me explain that. So if this is my sphere, okay, and I want to calculate my gravitational potential at this point, okay, so then this is R. Okay. Now, if I want to calculate the gravitational potential here, what this will be? This is smaller. This whole distance is smaller. So if this is h, so r is equals to capital plus r plus h. Yeah, simple. Okay, so the potential will not stop just at the surface, right? The gravitational potential will continue up to infinity, isn't it? It will be smaller in intensity, but it will still be there as per the Laplace's theorem. You know about Laplace's theorem about any field. We're going to discuss it in a bit with I mean, not very what is that called, in a vivid way, but we will touch upon it. But you know, any field, it will not lose its strength. uh, I mean, the strength of a field actually continues all the way up to infinity, right? So hence, did it answer your question?
Yes, sir.
Now, so this essentially accounts for the ellipsoid. Now, things get a bit more complicated now. So I can write down I is equals to, now let us say A and B is equals to, A is equals to B, okay? Let's just have that, uh, mm, let's just have that uh, assumption also in place. Now, then I can be expressed as A sine squared theta plus C squared theta. So then we can further, uh, you know, rewrite the equation as UG is equals to minus G capital E by R. So that is my, for the perfect sphere, minus, I'm just uh, replacing I with um, in the polar coordinate system with respect to theta. I can write down G T minus A T cos squared theta minus 1 cube. Okay. Now, this function, this particular function, T cos squared theta minus 1 by 2 is a second order polynomial of cos theta. Okay. Is a second order polynomial in cos theta. Okay. And can be written as, and this can be written as P2 cos theta. 2 stands for the second order polynomial. Okay. And it belongs to the family of functions which we call as, which belongs the family of functions called, do you know what it is called? Anyone?
Legendary polynomial.
Yeah, Legendre's polynomial. Yeah, Legendre's polynomial. So if you don't know what Legendre's polynomial is, in Lowry's book there is a small section given on the introduction of Legendre's polynomial. But of course, if you want to understand bit more than that, of course you can uh, study any basic mathematics book. Okay. So if I essentially express now this particular term with Legendre's polynomial, I can write down UG is equals to minus GE by R minus GC minus A. Okay, let me just do it in a new paper so that, because I have to do a bit more of derivation. UG is equals to minus E by R minus G C minus A R cube T2 cos theta. I can further, simplify this equation as minus G E by R 1 minus T minus A by E R square. Here capital R is the radius of the earth, okay? The radius of the earth, thinking it to be perfect sphere. Capital R by small r whole square T2 cos theta. Let me just close all the brackets. Right. Now, the potential theory requires that gravitational potential of the spheroidal Earth must satisfy an important equation, and that is what we called as Laplace's equation. So, the Laplace's equation essentially, that I'm sure you know about it. The Laplace's equation, the general form of Laplace's equation for uh, you know for the gravitational field, we can say that the second derivative, so t square ug by delta x square plus delta square ug delta y square delta square ug by delta z square is equals to 0. So this is the in the Cartesian coordinate, the Laplace's equation for the gravitational field. Okay? And in layman's term, what you can say that this is the gravitational field is like you have a. I'm trying to explain this equation in physical terms, okay, which is important for us to understand. That suppose this is my Earth, okay, and then of course the intensity of the gravitational field, yeah, becomes weaker, okay, as we move away from the Earth. Okay, so the intensity of the gravitational field becomes weaker as we move away from the Earth. and it becomes 0 at infinity. Right? So any equation that we put forward for defining UG, okay, that must satisfy the Laplace's equation. Now, so the solution of this equation, so what I have done here, you can see that I have only expressed it up to the second order polynomial, right? Up to the second order polynomial. Okay? But that will not be sufficient to actually accommodate for the uh, Laplace equation. So we need to expand it further. We need to expand it till infinity, okay, where I can say if R is infinity, UG will become 0. Okay? We have to go all the way up to infinity. So, so that I can say when small r is equals to infinity and my UG will be 0. So that is what, hence I cannot just simply stop at P2. I have to expand it further. So I have to write UG in more general term. So if I do that, what I will write down, UG is equals to minus G capital E by R 1 minus, see what I'm doing here, n equals to 2 to infinity, capital R by small r to the power n, Jn Pn cos theta. Okay? And I will now explain this particular equation physically. What does it mean? Okay. So to do that, what I have to do, what I'm doing, I'll just remove this part and then write this equation down and then explain it physically what it means. Okay. Let's write that down. UG is equals to minus G E by R 1 minus n equals to 2 to infinity, capital R by small r to the power n, Jn Pn cos theta. Okay. Right. Now, why it is, let's try to see the G minus R, you know, and this is the other term I have expressed in. I have expressed the Legendre's polynomial in its general form. Now, what I have to understand that why it is 2 to infinity. 2 is because we will see it in the Legendre's polynomial. It is always, you know, uh, it's if it is 2, this becomes the first term becomes r square. Okay, so the first, so if n equals to 2, I get to the elliptical term. Okay, and then if n equals to 3, 4, 5, 6, we will okay, I'm not explaining it properly. Let me try once more to explain this one. Okay. Now, if j equals to 2, if n equals to 2, so why I have to go to infinity, I have explained, because I need to satisfy my satisfy Laplace's equation. Okay. Now, if j equals to 2, yeah, what I will find out equals to 2 means that this is C minus A by R square. Okay. Yeah. And that comes around 108.2.6 into 10 to the power minus 6. Okay. If j equals to 3, sorry, if n equals to 3, then I will find out J3 is equals to minus 2.54 into 10 to the power minus 6. If j equals to 4, so n equals to 4, then J4 will be equals to minus 1.59 into 10 to the power minus 6. Okay. So now let me try to explain it once more. Let's write these figures down. And try to understand that in a better way. So J2 is equals to 1082 into 10 to the power minus 6. J3 is equals to minus 2.54 into power minus 6. And J4 is equals to minus 1.59 to 10 to the power 10 to the power minus 6. Now let's try to understand what it means. Okay, and we said J2 is equals to C minus A by ER square, right? This is E minus A. Now let us say I had my perfect sphere. Okay. I had my perfect sphere. And I can express UG is equals to minus E by R. Okay. Now this in the second place, what I do, I deviate from a perfect sphere and I become an ellipse. Okay. I deviate from my perfect sphere and I become my ellipse. So how would I accommodate that? What I will do, I will essentially have my UG for a perfect sphere. So that is my UG for a perfect sphere minus I will use this term J2. Okay, I'll use this term J2. Now let us, so as I said, you remember when we had drawn this picture of the, when we had drawn this picture of this reference ellipsoid, you remember that we said it's a best fit line. So best fit line means it's not the perfect line, right? So maybe we can increase the correlation and we can go for a more perfect shape. Okay, and that is perhaps looks something like this. Okay, we are getting more closer to the perfection. So to accommodate that, what I will do, UG perfect sphere minus J2 minus J3. Okay, and then I go another step forward. Okay, and then I again draw, I become more close to reality. Okay, and then that will be UG perfect sphere minus J2 minus J3 minus J4. And this will continue. We will never be able to reach to the absolute reality, right? But we can go close to the reality by increasing the number of n. I mean, increasing the value of n, we can go closer to the reality of the shape of the Earth. Okay, and you can see that when I am considering it to be a perfect sphere, then it is g minus g by r. So the value of g2 is exponentially higher than j3, and then the difference between j3 and j4 is not that much. If you calculate j5, it will be, the difference will be even lesser, but the difference between j2 and j3 is quite significant. Okay, so what do I mean by that? That at each of these places, at each of these steps, the increment is going to be smaller and smaller and smaller and smaller. Okay, so what do I, if I just simply draw, suppose this is my reality. Okay, and this is my spherical Earth, and here I am increasing the number of j. I mean, the coefficient of j is increasing. So what I will go in the first step, I have a very steep jump. Okay, so this is accounted for j2, and then this is perhaps accounted for j3, and then I will, keep on being close to the reality, but we will never reach the reality. Okay, so we said, you remember, in the to accommodate for j. So so this was my perfect sphere. Bring it to the enough. This is perfect sphere, and then we said this is my international reference ellipsoid. We said this is, this distance is 14.2 kilometers, and we said this distance is 7.1 kilometers. Okay, so this adjustment that we are doing from the sphere to the international reference ellipsoid is attributed to j2. Similarly, you know if we go further, so this is my perfect sphere, and then I'm looking into more, I mean, a shape which is closer to the Earth. Sorry, let me draw it once more. Sorry, this is IRE, the reference ellipse. Goes down. Let's go up again. Go up again. difficult thing to draw. It did something very funny. Let me just try once more. Okay, I don't need to link to shape. Of course, I cannot essentially do it here. So suppose this is my international reference ellipsoid, and then there will be, I'm getting closer to the shape of the Earth. Okay, it's not a perfect drawing, but you can think of it. So this is my international reference ellipsoid. Okay, and now I am accounting for J3. So this is around 16.5 kilometers here. Okay. Maybe here it is around 7.3 kilometers, so on and so forth. So if we keep on introducing J2, J3, J4, J5, J6, what we will do, we will get closer to the actual shape of the Earth. Okay? So, yeah. So, all practical purposes, we can stop at J2, and we can think that uh, international reference ellipsoid is a true representation of the Earth. I mean, most approximate representation of the Earth. But then, for our purposes as geophysicists, we might go all the way up to J3, where we are actually concerned about such undulations, okay, which represents the deviation of the actual shape of the Earth from um, from the from the international reference ellipsoid.
Uh, Excuse me, sir.
Yes, yes. Now I will take questions. Please go ahead.
Okay. So I had this doubt कि
Yeah,
when we talk about center of mass, okay.
yeah.
So center of mass of Earth would be different than the center of mass of this ellipsoid.
I mean, it's very close to the center of the. I mean, the ellipsoid is the Earth itself, right?
Yeah.
I mean, this
So
is the particular perfect shape of the. I mean, this is the shape of the Earth itself. So it will be. I mean, it will be very close to the center of the Earth. Yeah.
and to be honest, I really didn't understand. Is there any much difference between a spheroid and an ellipsoid?
There is a lot of difference between a spheroid and an ellipsoid.
Sir, I didn't understand. कि क्या है.
So spheroid means all the spheroid means it has an uniform R, right, everywhere. R, if you connect from the center of the Earth, it will be R from everywhere, right? That's a spheroid. And ellipsoid is an ellipsoid. So it has a major axis and it has a minor axis. The major axis and the minor axis is different from each other. Okay? So if I take a cross section of a spheroid, I will create a sphere. And if I take a cross section of an ellipsoid, I will create an ellipse. What's difficult in that? Yes, I'm not too sure if I'm understanding your question correctly.
So, like, I think I won't be able to explain. Ki, I'll tell you later. matlab, if I in a mail or something. Is it I'm not able to understand.
Okay, no, I mean we can talk right now as well. Okay, if you are comfortable in writing an email, or if you have a question, you can also yeah, you can call me as well during the
Yes.
office time, of course. Okay. All right. Anything else? I know this is the concept, to develop the concept is bit difficult. Now we have a lot of mathematics coming in, as well as the concept is a bit difficult to grasp at the first instance. But I hope I could explain at least 60 or 70% of it is clear to you. So what you have to do now is to read. Read the text again and again. Read multiple books, and hopefully it will be clearer to you. Okay. Once you understand the Legendre's polynomial bit more, and your Laplace's equation bit more, it will be even more clearer. Yeah, Om, you have a
Uh,
question.
so does that mean that the higher orders of J are added as we attain more precise instruments to
Absolutely, absolutely.
detect?
Yeah, the spheroid has a radius A and B, while ellipsoid A, B, C are different. Yeah, yeah, that's true. Is that a question, or is it something you answered to Yash, Kavin?
Just to make it clear, like I
Yeah,
also
yeah,
had it. So I mean,
yeah,
I imagined it this way, but just to make sure if it is correct.
yeah. That's right. That's right. Yeah. So it's absolutely true, Om, that what you said, that yes. So if we increase the order of n, I mean increase the order of j by increasing the number of n, we are getting closer to the reality. Okay, and that's why I tried to draw this one. Maybe I'll draw once more. That yes. So suppose, okay, I'm drawing here UG, okay, and here I'm drawing JN. Okay, I'm plotting JN. So here is UG for spherical Earth. Okay, which is T by R, right? And this is the UG, which is the reality. Okay, because Earth is not a sphere. Now we know Earth is not a sphere. It has a lots of undulations here and there. Okay, but how would you account for that? What you can do? You can go to J2. So here is J2. Okay, and I do a AB jump. I reach here. Okay, and this refers to the UG, which is related to IRE, International Reference Ellipsoid, which is obtained by drawing a best fit line through the GPS values that we have obtained, right, for individual locations of the Earth. And then we go to J3, we come here, J4 we come here, J5 we come here, but it never touches as well, you see, it never touches the reality. So it becomes like, kind of like this. It will reach the reality when J is equals to infinity. Okay, when I go to J infinity, then I'll touch my reality. Okay. So, but at each step, by increasing the number of J, yeah, but by increasing the number of n, hence increasing the coefficient of J, what I'm going one step closer to the reality. Okay. I think I'm off my time. So if you have any other question, just quickly 1 minute and then I'll stop.
So the orders of J are not increasing due to a specific component. For example, like the jump from J2 to J3 is maybe due to geochemical fractionation
No,
inside.
no, 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 absolutely not. It's your perception. It
Okay.
has nothing to do with what the reality is. Reality, it is there already. It is how we are perceiving the reality. Whether we are perceiving the shape of the Earth as a sphere, or whether we are perceiving the shape of the Earth as an ellipse, or we are getting into higher order of J and
Okay.
trying to go closer to the reality. So all the geochemical stuff, all the geophysical distribution, whatever reality is there, I mean, we cannot change it. It's our perception that we are changing by increasing the number of J. I mean, increasing the coefficient of J.
Got it.
Okay.
Yes.
All right, then I will stop the lecture here, and we will continue. In the next class, of course, in the pre-recorded lecture, in the overview weekend, I will start upon the actual geophysical technique. Thank you.